Okay, this is lab 2-9, balanced 3-wire circuits. The objective is to demonstrate basic current and voltage relationships in a balanced 3-wire or balanced single-phase 3-wire circuit. We need our bench, we need cone heaters, we need a light bulb, we need a clamp-on ammeter, a multimeter, and jumpers. So the purpose of this lab is electrical energy is transmitted over long distances with minimal loss by stepping up the voltages. At the consumer end, this high voltage is too dangerous, so the voltage is stepped down again for utilization to try to improve the efficiency at the low voltage end and to reduce the amount of copper required. A single-phase 3-wire system was developed. In this type of circuit, one conductor may be shared by 2 circuits. This arrangement is the safest and most efficient when the loads in the 2 circuits are balanced. In this lab, you will demonstrate how the circuit behaves when it is balanced. Procedure: we ensure that that's off. Using a supply bench, connect the 3-wire circuit as shown in figure 1. Use longer leads for the line and neutral connections so that extra turns may be used to connect the clamp-on ammeter for accurate measurements. Do not energize the circuit. The next page in your lab book shows us that we have 2 cone heaters connected up in a 3-wire circuit. You'll notice that actually for the first time I'm utilizing this auto transformer up here. This is the only way for us to convert a 3-phase system into a single-phase system again. Okay, so that we actually get currents that are in phase with each other. So they ask us to do some calculations. They say using a 660 watt 120 volt rating cone heaters up top there, connect the nominal resistance of the cone, calculate the nominal resistance of the cone heaters. So I use R is equal to E squared over P. 120 squared divided by 660 watts gives me roughly 22 ohms. So that's what I use to calculate. Okay, and then assuming that we had a 120 240 volt supply, calculate the following values. Okay, so if I've got this cone heater connected in series with that one, but also having the neutral, and we know that these cone heaters are the same rating, so it should be a balanced situation. Across one cone heater, if I estimated that the supply to it would be 120, we could divide 120 by 22, and that gave me roughly 5.5 amps of current heading to that cone heater, and then another 5.5 amps heading of current heading to this cone heater. However, we know that our supply voltage is going to be less than the 120, so I don't anticipate seeing exactly the 5.5 amps in this circuit. Okay, voltages that I expect to see, or I should say we should, if it's balanced, we should have 0 current on the neutral. I should then expect to see 120 and 120 across here. However, I don't think I'm going to see that. I think maybe I'll see about 110 or 111 volts. Okay, I have a voltmeter connected across the output of the source here. We'll see where that gets up to. And then I have another multimeter and my clamp-on meter that I can utilize in order to determine the actual voltage values and current values. So away we go. Power it up. I'm going to energize my variable supply up. Get it as high as we can possibly go. So we're getting roughly 208 coming out of this. Okay, coming output of that. So that means we have roughly 104 here and 104 there. Okay, so source voltages, line to neutral or line 1 to neutral. Let's just see if I can put that up there. I'm in volts AC. I'm going to go line 1 to neutral, and I've got 104, basically 105 there, and line 2 to neutral, I've got roughly the 105 there again, or 104 and a half. We can do it 104 and a half. And then line to line we had 209. Okay, next page. I guess I've already done the load voltages because that's where I took my line to neutrals and line to neutrals. So they are going to be exactly the same. They're the 104 and a half. Okay, now we can measure the currents. Click on my clamp-on ammeter to AC amps. Okay, and they want to know the current at line 1. So that's this guy here, heading up top here. Remember, we estimated about 5.5. we're lower than that now. We're at 4.8, and the reason for that is our voltage is lower. Okay, so we have 4.8 there on line 1. Line 2, I should have roughly 4.8 there again, which I've got 4.7, flickering a little bit, maybe up to 4.8. Okay, and my neutral should be near 0. And we have that at 0. Okay, so that tells me that that's a balanced circuit. Okay, so we're going to go 4.8, 4.8, and 0 are my answers for that. All right, then they ask us to shut this off. They then ask us to interrupt the neutral supply and install a light bulb. Actually, we're just going to go over to this 200 watt light bulb over here. That way I don't have to unscrew anything. And then we're going to come back to that neutral point, which is the same as over here, and put that there. So the expectation would be, if this is balanced, we know we have no current flowing on that neutral, so that light bulb should be off. So if I power everything back up again, okay, it shows me that I've got no current on that neutral. The source voltages, once again, they're going to ask us to take those readings. So line 1 to neutral, we've still got our 104.5. Line 2 to neutral, 104.5. Line to line, 209. Okay. Cone heater 1 will be 104.5 again. Cone heater 2, 104.5 again. So we're good there. Okay. So 104.5, 104.5, 209, 104.5. You get what I'm talking about here. Flipping the page, 104.5, and then the neutral resistance voltage. Okay, so anything across the 200 watt lamp, we should see nothing here, which we got roughly 0.2, which is near nothing. So call that 0. And then my currents should be the same as what we had, roughly 4.8, 4.8, and 0 on that neutral. Okay? All right? Next, what they're going to ask us to do, we power down, and we're going to open the neutral up. And in doing so, we're going to prove that with a balanced 3-wire circuit, we don't anticipate to see any potential difference between that neutral point and there, because it's balanced, okay? Because we had the 104.5 and 104.5 there, these are equal, so we should get nothing across that open, all right? So if I went line 1 to neutral, here still, we're going to be the 104.5, line 2 to neutral, 104.5. And then if I went across the break, we've got, they say about a 0.5 volt there, but it's technically 0. Okay. All right, the currents shouldn't have changed. My load voltages won't have changed, so I'm not going to take time repeating that. I'm going to measure the current again though. We're still sitting at 4.8 and 4.8. Okay. And of course no current on the neutral because it has no connection to come back to it. All right? And that is the end of that lab. We'll see you in the Learning Hub, and we'll go through the observations and conclusions for lab 2-9. Thank you.